Okay, there is. Now, these are the two formulas we have been using in the past classes. The derivative of the natural exponential is the exponential itself times u prime, assuming u is a function of x. And the derivative of the natural log is the reciprocal of the argument times the derivative of the argument. So these rules are the ones we have been using. And to face the problems we're going to solve now, we're going to use this property. The exponential and the log are inverse functions. So what does mean that? If you make the compositions e to the ln x, they cancel out and then you get the x. Or if you take ln of e to the x, you get the x. Okay. If we remember our pre-calculus classes, right? The exponential is something like this, e to the x. But e is 2.7128. It's a strange number that comes from some considerations that we have not covered and we have not the time. But this is the power. So we can put 27128 and some numbers to the x, and this is what we see. But also we can have, for instance, 2 to the x. 2 to the x is possibly more natural than this because 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, and so on, correct? And if we plot this one, we're going to see that it's pretty much the same kind of graph, correct? They are very similar. All the exponentials look very similar. If we take fx equals 4 to the x, obviously this is going to grow faster, so 4 to the x is going to be something like this. So, yeah, the exponentials with base different than the natural base are also differentiable functions because they are, we can say, parallel to the natural exponential. But the situation is, how do we get, for instance, this? What is the derivative of 2 to the x? What is the derivative of 4 to the x? Right? What happened with these derivatives? This is, well, is what we are going to discover today. So we are going to use these formulas, these properties, right, in order to find these derivatives, correct? So this is what we are going to do today. Okay, let me just then erase this portion, yeah, and assume that we have any function. So let an exponential function define a to the x, correct? Where a is a positive number, right? And is different than 1. So this could be 1.5, this could be 2, 3, 5.7, 10. Any number can be except 1 because this is a constant. A to the 1 is always 1. So this is the exponential function. This is exponential function. Okay, so the idea is, how can we get the derivative of a to the x? So that's my point. How can I get the derivative of this exponential, correct? Okay, I'm going to do a trick. So a to the x, right, is going to be, I'm going to use one of these properties, okay? This one. So I'm going to use the first one. So I'm going to change this exponential by other exponential. So I'm going to do e to the ln of a to the x. You see? By these properties, I know that the e and the ln cancels and I get the x back. So really, I'm not doing anything here. Just I put the e, the ln, these two cancel, so I get the a to the x back. But this is going to be my tree because I'm going to use the properties of the logs. What is this? It's very simple. It's the e, and because the log let me put this exponent at the front, I'm going to have x times ln a. Okay? So this is going to be the algebraic trick I'm going to use. E to a to the x is e to the ln to the ax of ax, and then I'm going to move this exponent at the front using the properties of the logs. Very simple. Now I'm going to take the derivative both sides. So I'm going to take derivative respect x of a to the x is the derivative respect x of e to the x ln a, correct? Ln a, right? So I'm going to use this property right here. The derivative of the exponential of a function of x is this times the derivative of the exponent. So it's what I'm going to do. This is going to be e to the x ln a times the derivative of this portion. This is a constant. Ln of a is a number, so I can put it at the front. And then I got the derivative of this, so this is going to be ln a. So the derivative of this expression is the derivative of this exponential. The derivative of the exponential, remember, is this one right here, e to the u, the same thing, times the derivative of this portion at the top. And because this is a constant, the derivative of the x is 1, so this is my derivative. Now, I'm going to return this to the original form. This is this, so this is going to be a to the x times ln a. So the formula that we discover now and we are going to use is very similar to this one right here. The derivative of any exponential function is the same exponential function, but the only thing is different is that you are going to multiply that derivative by the natural log of the base. This base could be 1.5, 3, 7.5, 10, 24. Any number is going to be taken the log, and then you are going to multiply times the original exponential. So the derivative we're going to be using now is derivative respect x of a to the x is ln a times a to the x. So that's going to be my new formula, okay? It's very simple. So with this one, right, with this, we can deal with different problems, correct? Let me just take a little board different than this one. So I'm going to use this board to make examples. It's a little one, right? So suppose I have the derivative respect x of 2 to the x. Okay. Well, that's not a problem. What I have to do is remember the formula I have to use, this one. So this is okay. The a is 2. This is the derivative of 2 to the x. So I have to put the ln of 2 times 2 to the x. So this is ln of 2 times 2 to the x. And that's my answer. If I have, for instance, the derivative respect x of the 10 to the x, right? Okay. So I have to do ln of 2 times ln of 10 times 10 to the x. That's it. So the derivative of the exponentials is very simple. Okay. So obviously we can have more complex problems. So the general rule is going to be derivative respect x of a to the u is going to be a to the u. Let me just put this one better. Ln a times a to the u, the derivative of the exponent. So this is going to be the general formula in case we have something like 2 to the x squared plus x. So if this is my function, if this is the exponential with this new formula, then I have to use the chain rule. I have to get this derivative of this exponential in the normal way as this one, but I have to multiply times the derivative of the function in the exponent. So in this case, if we want f prime of x equals, well, ln 2, that's the ln of the base, 2 to the x squared plus x times the derivative of this is 2x plus 1. And this is the derivative of this function. So it's not really difficult to get derivatives of exponentials, right? As you see. Okay. Any question or problem with this? I guess it's very simple. Okay. Let me just do, for instance, another example, a little bit more complex, right? So we have, for instance, the fx is cosine x times 2 to the x squared plus 10 to the cosine x. I'm inventing a strange function to work with, correct? Okay, suppose I want the derivative of this strange function. What is f prime? It's okay. So I have to use the rules I learned. The derivative of the addition of two things is the derivative of this, the derivative of this. Okay, then this is a product. So I have to take this derivative times this plus this times this derivative. And this is the formula I just discovered I have to use, correct? So, no big deal. I'm going to take f prime of x is derivative of this cosine, negative sine, times 2 to the x squared plus this function, cosine x, times the derivative of this. This is, well, I have to take the natural log of the base times the original function times the derivative of the function at the exponent. Plus, now I have to do this, okay? What is the derivative of that? Okay, the derivative of this is the natural log of 10 times the exponential function times the derivative of the exponent, negative sine x. Okay? So, we can simplify a little bit this. This is, well, possibly. Let's see what can we group. Sine x here, 2 to the x squared. Well, we can group this together. And, well, we can put this one. So the algebra coming x is up to you. Let me just don't do too much. So it's negative sine x, 2 to the x squared, plus 2x times cosine x, ln 2 times 2 to the x squared, plus, well, minus sine x times ln 10 times 10 to the cosine x. So, as I told you in other situations, the derivatives are pretty simple, right, to get, because it's the application of the rules of differentiation, one after the other one, until you get a final answer. As you see, this is very different than integration, that you have to check, okay, which can be my u, and what is the du? Okay, I have to guess this other option, until you get the match you need. But in the case of the derivative, this is very simple, correct? This is just the application on one thing after the other one. Okay? So, any question about this one? Okay. I have been having a lot of messages from the math department. I don't know what's going on, but I guess I'm going to stop right here, right? And